Hey guys, welcome to another lesson. Today, we're going to do the proofs topic in the Extension 2 syllabus where we'll cover the concepts relating to contrapositives, contradiction, negation, etc. That topic, some people consider to be quite challenging because of the newness of it all, right? It's still new compared to things like mathematical induction in proofs or inequality. So let's go down. I'm picturing about 2 lessons where I'll split the video into 2 parts. First part covering on definitions and contrapositives, and the second video covering contradiction. Now, if you haven't already done so, please subscribe to the channel, like the video, tell your friends. Let's get started now. With this topic, I'd like to begin with definitions because it's actually quite crucial, and just to talk about the types of questions you'll see in this topic. So let's begin. Let me zoom right in with proofs. So for proofs, there's maybe 2 sub-bullet points worth noting, right? First one's definitions. Yeah. First one's definition. Now, the proofs topic, by the way, has other parts like inequalities and induction. I won't do those, right? Maybe I'll save those for another video, but for now, let's just do the initial sort of definitions of converse. Let's start there, right? So converse is defined as for a statement, for a statement. So make up a statement where P implies Q, right? That's a statement. The converse or the reverse statement or converse is Q implying P, right? Now you can write it like that. I like to write it like this if that's okay with you. So P and Q, and the arrow goes backwards, right? So that's a converse where Q implies P. Pretty easy. Now let's talk about equivalence. Yeah, equivalence. And there's a really nice past paper question that I'm going to start with right after we do this these theory points, where it actually talks to every single one of these definitions. It's a nice one just to sort of canvas the types of the words that you get, the new terminology you get in this topic. Now, equivalence, when a statement P implying Q and its converse Q implying P is true, right? That is equivalence. Yeah. Now, or you can say that P and Q imply each other. That is a ultra strong statement, actually, because a lot of the times you can prove the statement going one way, but to prove it back, that's where it falls short, right? That's when you can say it's not equivalent. But if it's equivalent, going one way and going back, both are true. Now, next word, pretty important word, actually, negation. Yeah, negation is essentially the opposite statement, right? Or the opposite event. Now, for negation, I want to give you this table, right? Which basically gives you the event, the opposite, or the negation, the event, the negation, right? Just to basically summarize some of the questions that have these elements. So if I say this is maybe call this one, this is a statement, and this is the negation, right? So the typical examples are, if I have now obviously let's start here, right? If I have a statement P, right, is true, then the negation is just not P, right? So there's 2 ways to write it. You can either write angle P, or you can write P bar, right? Same thing. Maybe for this today's lesson, I'll use angle, right? So what about P union with Q, right? Now, P union with Q, or P or Q, right? The opposite is not P and or intersecting with not Q, right? that's the opposite negation effect. Similarly, right, so just to be clear, right, the way you remember it is whenever there's union, intersection is the opposite. And then you basically oppose, like find the opposition for both of these, right? The opposite case for P and Q. Yeah, that's how you sort of come to that. So similarly, if I said to you P intersecting with Q, same deal here, right? Not P, union now with not Q, right? Is that okay? Now, and the last two that I want to sort of talk about is you'll see the symbol for or X, P is true. Then we go, the opposite event if for all X, P is true, then there exists an X where P is not true, right? That's the opposite event. And similarly, if there exists one X where the statement of P is true, then the opposite of that is for all X, yeah, P is not true. Yeah, that table's cool. I always like to get my students to write that down and sort of stick it somewhere because that comes to play in a lot of questions where there's symbols involved. That's a really good place to sort of reference to. Now, how much space do I have? Okay, a little bit more space. So I'm going to say counterexamples, right? That's a very common type of thing for you to need to explore. Counterexamples. Yeah. It's just an example that disproves the statement. Yeah. And I've got two more. Now the next two are actually, let me see if I can fit them. No, I can't fit them. I won't fit them down there. Guys, next page. Yeah, the next two are actually super crucial. In fact, I'll put it in a category of its own, right? I'll put it in sub-bullet point 2 because there's questions that are chunky relating to the next two, right? And I'll put it as ways to prove a statement. So in this topic, what you'll actually find is that the ones that I talked about before, negation, equivalence, and all that, a lot of questions are like, state the negation, state the equivalence, state the converse, or give me a counterexample, right? That's like a one-liner for 1 mark, right? For the next ones, generally they're like 2-3 marks, right? So the first one is what they call the contrapositive. Yeah, so the contrapositive is a thing, but it's also a method, right? To prove a statement. Sometimes it's also known as a contraposition, right? Same thing. Yeah, exactly the same thing. And the contraposition is when you prove this, the contrapositive, right? Which is the opposite event. So if I wanted P to Q, right? Actually, so to prove a statement, P implying Q, right? Maybe I'll give that as a heading. Then the contrapositive would be not Q implying not P, right? That's a contrapositive. So a lot of the times in the questions that they want you to prove, the contrapositive is actually easier to prove and the statement itself is actually hard. So that's why they go, can you please use the contrapositive to prove the statement, right? Once you prove that, that implies, right, this guy is equal to P implying Q, right? That's really what that statement's all about. Now, the last one, which is a very classical question, proof by contradiction. Yeah. So the proof by contradiction is basically you prove P to Q by showing that the negation is illogical. Yeah. So it's like saying, I assume the opposite is true. Oh, it doesn't make sense. So therefore, my original statement is true. That's contradiction. And we'll do that in the next video. All right, guys, that's enough sort of definitional talk for me. Let's dive into some past papers and really bring this to life, right? So first question from Askham. Askham 2022. Now, I like this. So basically, in this Askham question, they give you a statement where they go, no, consider the statement. Yeah, for all A, that is real, right? That's important. For all A, that's real. If sine A equals to K, then sine inverse of K equals to A, right? So they're saying if sine A equals to K, then if I inverse that, then that equals to A as well. Now, look at the questions. Converse, contrapositive, negation, equivalence, right? There it is. I don't know why they're 2 marks each, right? It feels like it's a lot of 10 marks for this question, because the last one there is determine whether it's true or not. If not, give a counterexample. Right? So if I can find a counterexample that disproves this, I'm done. So I like this question because it just cuts across all the definitions, right? Just to make sure you know what they are. I'm not sure about the 2 marks each, but I'll take it, right? If I went to ask him, definitely take it. Now, let's do this, right? So part 1, write the converse. So I want the opposite event, right? So the opposite event basically says you still assume everything up until the statement that is with the if, and then you'd go opposite on the statement itself, the one that they imply. So part 1, right? So the way I would write this is the opposite. Sorry, the reverse of this is for all A that's real, right? Still go there. Right now, in terms of the definitions that I had, this is like event P, and this is right now like event Q, right? And the then is basically the implication sign, right? So then the converse will be Q implies P. So I go inverse of K equals to A, then sine A equals to K. In fact, I'll slot in the word if in here, right? If that, then that, right? Pretty straightforward. That's the convert. That's 2 marks, right? Very generous of asking for this one. Number 2. Now contrapositive, right? Contrapositives. So converse was Q implies P. Contrapositive is not Q implies not P, right? Not Q implies not P. So contrapositive is for all A that is an element of the real number set. Yeah. If not Q, right? The opposite of Q. So if sine inverse of A doesn't imply, oh, sorry, K rather, doesn't equal to A, then sine A doesn't equal to K, right? So basically opposite events for both, switch them, implication, right? Is that okay? Yeah, so that's 2 marks as well. Number 3, right? Negation. So I want something that's the opposite of this. Now, the way you do negation, sorry, that's what I was trying to describe with this black line here, right? Negation, you assume everything at the start is true, and then you assume that the thing that it implies is false, right? So you go, oh, no, that's a lie. So for negation, let's come back to this table, right? So whenever we see a for all, the negation is there exists, right? Yeah. So for all, there exists. That's the opposite. So let's go back. So negation in this case is there exists, right? There exists an A, which is an element of the real number set, right? Where, yeah, there exists an A, so that if sine A equals to K, right? So that where there's P, then Q doesn't exist, right? Q is false. So sine inverse of K doesn't equal to A. So it's basically saying there is an A that if this happened, then Q doesn't happen, right? That's the opposite event, right? That's the opposite event. So please get into your systems that the opposite of for all is there exists. And in this case, I wanted Q to fail. Right? It wasn't about P. P is always like, if P happens, Q fails, that's the opposite event. Yep. Now, 4. Equivalence. Equivalence is a really strong statement, right? Equivalence basically says P implies Q and Q implies P, right? Or going backwards. Maybe I'll just write like this, right? Going left to right. Yeah. So both of those need to be true. So in this case, right, I think the best way to do this, and I was talking to my students about this question. I actually, by proving that equivalence, I'm going to prove equivalence doesn't hold in this case. But by doing so, I actually use a counterexample to prove it. So I actually do questions 4 and 5 at the same time, right? I'll show you what I mean by that. So in this case now, let's really explore the first statement. So when P implies Q, right? So that's the original statement. I'm saying that if sine A equals, I'm just repeating the question, right? Then sine inverse of K equals to A. Now, let's explore an example, right? And I'll use green to show this, right? So let's say, for example, if sine A, or let's say sine M theta, or let's A B theta, equals to a half. Yeah, now I know that inverse sine, right? So inverse sine of a half equals 2. Yeah, if I shift sign that on my calculator, right? What do I get? What angles can I get? I can get pi on 6, but I know using all stations as central, angles of any magnitude, I can get one. There's infinite solutions, but there's another one in the second quadrant. So pi minus that, 5 pi on 6, right? So I'm going to assume, right? Let's go and assume that this guy's A, right? So I don't need all the answers. So let me say this again. This is how I'm going to play it out, right? So I'm going to assume theta was 5 pi on 6. I can see it there. That's an answer. Sine 5 pi on 6, and I'm going to delete this guy, 5 pi on 6. Perfect, right? I'll just write 5 pi on 6 here. Because 5 pi on 6 is the one that doesn't work, and I'll show you why. So in this case, I've let A equal to this as an example, and K equals to a half. So the inverse sine of K, which is inverse sine of a half, equals to 5 pi on 6. That makes sense, right? That makes sense. But let's look at the opposite, right? Yeah. Now let's look at the opposite. So Q, or the reverse, sorry, P, if sine inverse of K equals to a half, so equals to A, then sine inverse, sorry, sine A equals to K. Right? Now, this one here, actually, the first statement fell, but let me explore this again, right? So if sine inverse of a half equals to 5 pi on 6, then sine, let me just write it all out, right? Sine 5 pi on 6 equals a half. Okay, now, the one that really fails, right? The one that really fails is this guy here, right? One of these fails. So let me see. If sine inverse of a half equals to this, then yes, this is true, right? Sorry, pink. This statement is true, absolutely, no doubt. Right? No doubt. And this one here isn't always the case, because I know, right? When sine of an angle, right? If sine of an angle, actually, no, this one's which one's fails? Sorry, bear with me. I think I got that the other way around. So if sine of an angle equals a half, then sine inverse equals to this, right? So if I shift sine that, perfect, right? No, that fails. I was right the first go, right? If sine that, then this, right? Then sine of this equals that, perfect. This one here fails. If sine of an angle, so maybe in this case, I'm going to replace, right? Replace the 5 on 6, right? With theta. Yeah. So if sine theta equals to a half, right? Then sine inverse of a half has to equal to a unique theta, right? That's really what that's trying to say. If this was theta, then this has to be a unique theta. We know that's false because I can think of, well, many examples, but in this case, right? Theta can be pi on 6, 5 pi on 6, etc. So even though I might plug in a unique answer here on 5 pi on 6, the inverse of sine half can have multiple solutions, right? So therefore, this is a false statement, right? That's not a full implication. So what am I trying to say? In this case, actually the equivalence fails because yes, your converse is true, but your original statement has an example which disproves it. And that's the example I'm going to use for part 5 as well in this case, right? So part 4, not equivalence, right? Because I can think of an example where the original statement fails. And in this case, right, not equivalence is driven by, so that's my answer for part 4, actually, right? And then part 5, using the same counterexample, the statement is actually false. So the way this question is written is kind of weird because what I would have done is actually just asked for and left it there because I can see that by proving that the statement is false, equivalence failed. So it's kind of strange that part 5 sort of asks you to prove that it's false again, right? Because the statement's already failed with a counterexample. So I guess what I'm trying to allude to here is that to do part 4, right? It's a very strong statement. Generally, I've seen questions where the failure is not actually the statement. The failure is actually the converse. So, but in this question, it's kind of weird because the converse passed, original statement actually failed, and then they're asking me to prove that the original statement fails again with a counterexample, which I already did in part 4. So, but guys, what I wanted to illustrate here is the definitions, right? Converse, that's the opposite event. Contrapositive, that is not Q implies not P. Negation, that's opposite, right? Yeah, and then for equivalence, I need both of these statements to be true. Sorry, I'm just going to delete the highlights now. I need both of those statements to be true. In this case, the original statement fails. Therefore, equivalence fails. And obviously then for part 5, the statement is false because the counterexample used in part 4 made it false, right? Is that okay? So guys, keep that in mind. Let's move on to another question, right? Like this question, cuts through all the definitions. Now, the next one from Gosford is a very quick example. So, but I wanted to show you the types of questions, right? Counterexample. I just need an example that disproves this, right? Now, I think the hardest thing about this question may be the symbols, right? Let's have a quick look, right? For all x that's real, there exists a y that's real, where this guy is false. So where this guy is true. I want to prove that this is false, right? So that false word belongs to the question, right? Because it says prove that is false, right? So I just need an example where right now I got x equals to y squared. All right. I just need to prove, put a number in that's false. What's important here is that x and y are real. So all I got to do really is sub in x is a negative number, right? Because then y squared has to be imaginary, right? So for example, let x equal to -1, right? In this case, right, -1 equals to y squared, y equals to plus minus I, right? Which is false. Which is false because y then would be a part of the complex number set, right? Is that okay? Right, it's imaginary, right? It's or you can say it's not part of the real number set. Yeah. Therefore, proposition is false. So with counterexamples, you just need an example, right? Let x equals to -1 in this case. Yeah, which basically says y isn't real because it's imaginary, therefore proposition false. 1 mark. Let's move on. Right, nothing too hard about that. Right, 1 mark in Gosford. Now, next one. So once again, very quick fire questions. Negation and then counterexample, right? Negation and counterexample. So for this negation, I need opposite elements, right? And it's really important for you to go through the symbols, right? So what's that say? For all x, that is a positive z integer, right? There exists a y that is a positive integer where this guy is true. I want opposites on all elements. Opposites on all elements, right? So for part one, I need opposite of that. So instead of for all x, I go, there exists an x that's part of the positive integer set, right? Where for all y, that is part of the positive integer set. This guy is false. Y doesn't equal to x minus 1, right? So opposite elements of each component, right? So that's why I needed that table there, just to show you how we go about doing this, right? Part two, prove that the original statement is false by having a counterexample, right? So I just need, for all x, there's a y. So I can make up an x, right? And make up a y value that says this guy's false. Yeah, so let's see. I think what's important here is that it says positive integers, right? Positive integers. So I can easily say now, and the way I'm going to sort of explain it is, that's a straight line. What's that? X minus 1, looks like that. Yeah. But this line here only exists when, oops, this guy's positive, right? I've got so many ways of disproving this. I can just sub in a negative number, right? If you sub in a negative number, it's wrong. Yeah. Sorry, when y is positive as well. So it's actually even longer, right? Yeah, I can sub in so many numbers, right? Negative numbers. So I can't sub in negatives. I got to sub in a positive x and a positive y value, right? All right. Positive plus y. So if I sub in x equals to 1, and for all, right? For all x, all positive x. So I can sub in any value from here onwards, right? And it'll disprove this. Yeah, because it's saying for all x, there is a y where this is true. Right? So for all x positive, there is a y where this is true. So sub in any positive x. Let's say x is 1, right? X is 1, because when x is 1, so let x equal to 1. When x equals 1, y equals to 1 minus 1, which is 0, and that's false, which is false, which is not, sorry. Yeah, because 0 is not part of the positive integer set. Yeah, it's not part of it's 0, right? So the moment I let it be 1, yeah, because they're saying for all x, there is a y where this is true. Well, actually, for this x, this y isn't true for this statement, right? Therefore, false. Yeah. Yeah. Does that make sense? So in this case, the trick here, or the key here is for all x, there is a y. So then you just go, well, okay, no, sorry, for all positive x, there is a y. Just choose any positive x. You can choose a half as well, right? That doesn't work. Actually, no, you can't choose a half because you need a positive integer. So actually 1 is the only case, right? 1 is the only case because if you choose 2, 3, 4, it'll work. 1 fails. It's actually the only one. Yeah. So 1's the only one because I need positive integers. Perfect. Right, that limits. That's good because then the marker only has one answer to go by, and it's positive 1. If they put a half or any other fraction is wrong. If they put negative integers, that's wrong as well because x has to be a positive integer, right? Anything bigger than 1, the statement's actually true. So 1 is the only counterexample to this. Guys, that is negation, counterexamples, etc. Let's do some chunkier questions where we talk about contrapositives and contrapositions, right? Where they need a bit more work and they're a bit more structured. Normally about 2-3 marks per question instead of the one-off question that we have here. So this question here from Sydney Grammar. Use proof by contraposition or contrapositive, same thing, to show that for x, which is an integer, if this guy is even, then this guy is odd, right? So in my structure, right, this guy here is P, this guy here is Q, right? And there's the implication that they want me to prove. So whenever you do contrapositives or contraposition, always define what the contraposition is and then try to prove it, right? So for example, in this case, right, and just to write it in pink, right, I wanna the contrapositive, I'll write position because this question says position. right? It's basically not Q implying not P, right? So in my answer, the contraposition would be not Q, right? The opposite Q. So X, you can say is not odd or is even, right? Is even. So maybe I'll go if, well, you can even write when X is an integer, if X is even, then X squared minus 6X plus 5 is odd, right? Both of those are opposite statements to P and Q, right? Sorry, I'm just going to disconnect this because this one move is over. Perfect. Yep, cool. So this element here, if X is even, then this guy's odd, right? Let's start there algebraically. So let X be even, which means let X equal to 2 times an integer M, right? Yeah, where M is an integer. Yeah, let it be integer. So once you do that, then I'm going to sub 2M into here, and hopefully it gives me an odd number, right? Let's have a look. So then, therefore, X squared minus 6X plus 5 equals 2M squared. I mean, the algebra isn't that hard, is it? 2M plus 5. Guys, I'm hoping that when I factorize the 2 out, there's an odd number remaining, right? So that's 4M squared. I can see it there, actually, 12M plus. Now I'm going to split the 5 into 4 plus 1. Yeah, with the sole aim of being able to factorize, right? Factorize a 2 from these ones, right? Take 2 out, 2M squared. I really don't care what's in the bracket as long as it's whole. 6M plus 2 plus 1. All right, there you have it, right? So then that equals to 2, and I'm going to replace, just notationally, this whole thing here with the letter N plus 1, yeah, where N equals to 2M squared minus 6M plus 2 is an integer. Yeah, since M is an integer. And so therefore, because of the plus 1, you can articulate that that guy is odd. So therefore, right, I've proven that my contrapositive or contraposition is true. Therefore, statement is true. Yeah, is that okay? That's how you do it. Basically, in this case, it's easier to prove the contraposition or contrapositive to be true than the original statement. That's how you sort of play it, right? Opposite of Q, then opposite of P. In this case, makes absolute sense, right? Let's do another one. Yeah, these guys are beefier, right? The next one, 3 marks from Ascom, right? Let me just zoom in. So, prove that the contrapositive by the contrapositive that if M and N are positive integers. Now, there's my starting if, right? If M and N are positive integers, oh no, that's not it. That's my, the bit before it. M and N are positive integers. Okay, but I'll highlight that. Sorry, that's part of my question. Such that M and N and M and N, N minus N, have no common factors. Then M and N have no common factors, right? So the first part here, actually, maybe I'll highlight in pink. This guy here have no common factors, and M and N have no common factors. So that's P, and this is Q, right? And that then implies, right? And they want contrapositive. So I know that my contrapositive in this case has to start with, okay, M and N are positive integers. So given that M and N are positive integers, yeah, then M plus N. Now I want opposite, I want Q. I want not Q implies not P, right? So M and N have no common factors. Opposite of that, they do have common factors. But the word and, right, is important. Right? So I need both of them, right, to have common factors. So M and N have no common factors. So I need the opposite of that, right? So let's go. So M and N have no common factors. I'm just going to write out the same, right? N and N have no common factors. Right. Let's see if this is right. Yeah, so. Yeah. Yep, cool. If M and N are integers with, oh no, that's not the opposite, right? That have a common factor, right? That's the opposite, right? This is Q. So just to really hammer home, I'm writing Q, not Q, right? Q is no common factors. M and N have a common factor. Perfect. Then, oh, this is very long. I'm just going to drop down the line. Then, yeah, M plus N and M minus N have a common factor. All right. And this guy here is not P. Yeah. So I'm going to assume that M and N have a common factor and then show that the sum and the difference have a common factor. Okay. Now, I guess the hardest thing about this is just understanding where to start and how to position this. Once you have this pink sort of statement, right? Let's start with the contrapositive. Let's start with not Q, right? So M and N, so let M equal to, now, how do I show that two numbers, M and N, have a common factor? So maybe let, I don't know, A, right? M equals to A times X, right? Where A is the common factor, and B, oh, so N equals to A times Y, right? Where A, right, is a common factor. So A, X, and Y are integers, right? Yeah, so if they're integers, then, and just be very explicit, right? Where that and A is the common factor. Yeah? Just be very explicit about it. I've got M equals to A times X, N equals to A times Y, both have A, they're common, right? Therefore, M plus N would equal to AX plus AY, which equals to AX plus Y, right? They have a common factor, right? Yeah, so factorized it. So they have a factor of A, and I know that M minus N equals to AX minus AY, which once again equals to AX minus Y, right? And they have a common factor there, right? Yeah. Therefore, oh, sorry. Maybe go therefore downstairs, right? Therefore, M plus N and M minus N. I mean, the algebra is so easy. It's just the concept, right? The setup of the proof, the layout, that's where it's hard. M plus N and M minus N have a common factor of A, therefore contrapositive is true. Right? So I've let my M and N have a common factor. I've proven that they both have a common factor. That's not Q. That's not P. Done. Contrapositive is true. Therefore, statement is true. Yeah. Now, when I say statement is true in a test, I would actually rewrite the whole question, right? But that's how you prove it. So in this question, for 3 marks, I think the hardest part is definitely this bit here, right? Just the setup of the question, because the algebra, I mean, come on, let's be honest, right? N plus n, n minus n, just factorize that out. That's not hard, right? It's the layout, guys. Let's do one more question, right? Of contrapositives where a bit harder, where there's cases involved. I thought I'd show you this because the first one, pretty straightforward. Second one, maybe just the structure of it, a bit harder. And the third one now, St. George Girls. All right. Let's see. Use a contrapositive to prove now. This one's important, right? The last question sort of, I thought it was going down the path because it says M and N, but it wasn't talking about M and N where there's sort of 2 mini events inside the queue. It's actually M and N have no common factors, that is Q. But the next one actually, I'll show you what I mean by that mini event, right? Use contrapositive to prove that if this guy is odd, if that is odd, then the integers x and y are odd. See how the word and there is important? So if I was to say this guy here is P and this guy here is Q, Q actually has 2 things in there. Q is made up of x and y are odd. Why am I telling you that? Because the opposite event of x and y are odd isn't x and y are even, it's x or y are even, right? Just be very careful with that because the contrapositive, let's state it, right? Let me state the contrapositive here. Yeah, the contrapositive is not Q, so integers x or y are not odd or even, right? And then, so this guy here is not Q, then not P is odd, right? So it is even, right? So that guy there is not P. But the key there is this word or, right? So how do I do or? I have to do cases. I have to do a case where x is even and prove that that's true, and then do a case where y is even and prove that that's true, right? So let's go down that path, right? So let x equal to 2 times m, where m is an integer. That makes it positive, right? Yeah. So once you do that, let's sub it all in. I'm hoping that my final answer has 2 factorizable, right? Let's see. Therefore, x squared, y squared, so this is my question, equals to sub the 2m into where the x is. So 2m squared times y squared minus 4y equals to, that's 4m squared, y squared minus 4y. And by the way, x and y are integers, right? So that's nice because all of these are integers, so I'll factorize the 2 out. Now I don't care really what's in here. That's 2m squared, y squared minus 4y. Everything there are operations with integers, so that just equals to 2n, where n equals to 2m squared times y squared minus 4y is an integer. And all the operations in integers done. Right? Yeah. Therefore, x squared y squared minus 4y is even. All right, that case is true. I'm going to do exactly the same case now. Let's see how much space I have. I'll move it over here. Right, let's move it over here. Let y equal to 2 p. I was going to say m, but let's use a different letter, where p is also an element of it. That's also an integer. Right? All right. In this case, x squared times y squared minus 4y, right, would equal to x squared. So I'm subbing into y now, right? It'll be 2p squared minus 4 times 2p. What am I after? I just need to factorize. I'll expand first. I just need a 2 to be taken out. That's 8p. Perfect. Yeah, don't need 4 taken out. I just need 2, right? X squared 2p squared minus 4p. Yeah, so I don't really care what's it. And then I go, well, that equals to 2 times q, where q equals to the square bracket of that. And everything here are operations with integers, right? Which makes that an integer. Yeah. Therefore, x squared y squared minus 4y is even also. I've done it, right? So I've considered when x is even, I've considered when y is even. That's the or statement, right? This guy or this guy. And I've proved that both of those give me the final, the expression I want as even. So therefore, my conclusion is, therefore, contrapositive is true. I might have one line space. One sec. Perfect. Therefore, statement is true. Guys, how was that? So what did we explore today? I wanted to cover definitions, right? The definitions here across the 4, and then methods by contrapositive and contradiction I'll do in the next video. Yeah, there's a lot more questions that are fairly, some are fairly straightforward, some are quite involved. Let's explore next video. The past papers, some of these are 1 marker where the definitions are involved, right? Actually, I say 1 marker. Askham went a bit nuts on these questions. I think each of these should be worth 1 mark. Don't know why they're worth 2. 1 mark, 1 mark. You see that across the board there. And then for the ones with contrapositive, 2 or 3 marks, depending on, I guess, the intensity or the commonality of the questions. Some of these are quite different, especially the cases one, a bit more involved. That's why they're 3 marks. Guys, hopefully that was okay. If you found that video useful, please like the video, subscribe to the channel, and tell your friends. I'll see you in the next video. Thank you.